This video is about motion graphs. Alright, so we're going to learn about motion graphs. Let's look at graphs in general. Now there are certain things about graphs that we use to describe things in physics. One of them is the slope. The slope is a measure of how steep the line in the graph is. Now you measure the slope as a change in y-axis over the change in x. Now change always means final minus initial. So if it's going downwards and your final is smaller, and you'll end up with a negative number. In this case, our final y is at 3. Our initial y is at 0. And if I'm looking for the slope of this part, then my final x is 3. And my initial x was 0. So it's 3 over 3. So I have a slope of 1. Okay, the other important part is the area under the curve. Alright, now the area under the curve is the same kind of idea as x times y. Now if we have a triangle, you need to remember to multiply that by 1/2. This in the red square is in your reference table. So if you ever can't remember how to find the area or something, those are important. Now when you're finding the area, you want to break it down. You want to find the area of the triangle and then the area of the square and add them together. Now let's look at motion in general. We use a few different things to define and to describe motion. X represents position. Where are you? Where are you in reference to a certain point? Okay? So you are 2 meters away from something. Now I use the units meters. The unit meters is the standard unit for position, and if you're not in meters, for example kilometers or centimeters, you have to convert into meters. The not, the 0 that's below the x, that's the symbol for initial. The starting, what happens at time equals 0? Where are you? Okay, and that's true for all of them. So if we keep going down and we look at v and v naught, then we have the initial and the final or current velocity. Okay, velocity is speed with direction included. And we'll get a little bit more into that later on. Alright, so how fast are you going? Your units are meters per second, and you must be in those units. Next, acceleration. Acceleration is how much you're speeding up and slowing down. You know, if you're in the car, how hard do you put on the gas? How hard do you put on the brakes? Okay? That's acceleration. Its units are meters per second squared, which is the same idea as meters per second divided by seconds. Lastly, time. Well, we're all very familiar with time. We never have enough of it. Time is measured in seconds. So as you can see, all these units are in meters and seconds. Okay, and time is just the measure of the length of time, I know using the word in the definition, between the initial and the final state. So between x and x naught. Some of you might be familiar with d for displacement. Displacement is just the change in x, which is x minus x naught. So how much did your position change? You can almost always set x naught equal to 0. Some people like to, some people don't. It changes a little bit how you approach something, but it is always an option. It just depends on where you decide that your initial position is, or your frame of reference is. There are two things. There are vectors and scalars. Vectors have magnitude and direction. That means that magnitude means they have a number, some value, and direction is shown in physics as a positive or negative. So if I'm going 2 meters per second east, then I'm going positive 2 meters per second. If I'm going 2 meters per second west, then I'm going negative 2 meters. We have a magnitude, 2, and a direction, negative. Alright, scalars have just magnitude, which means they don't have a negative value. They have no direction. Time is an example of scalar. There's no such thing as negative time. Mass is another thing. You're not going to weigh negative 20 kilograms. It's just not going to happen. Now, we use conventions for directions. Anything north, up, east, or right is positive. Anything west, left, south, or down is negative. Okay? Now, let's look at graphs in physics. We said we like the slope and we like the area. Let's look at slope. Now, we have a position time graph, which means there's an x and a t. It's a position time graph. Now, if we were to solve for the slope of it, we would solve for the change in x over the change in t. Now, x has a unit of meters. So you would have an answer ending in meters. Time has a unit of seconds, so you'd have an answer in the form of seconds. Meters per second is velocity. So the slope of a position time graph is your velocity. Now, if you have a VT graph, a velocity time graph, you do the same idea, but you get meters per second squared. So then the slope of your VT graph is your acceleration. If we look at area, area is x times y. So if I look, I'm just going to look for the area of, let's say, this part right here, because if it's different shapes, we got to break them up. Well, it's meters per second times seconds. Our units multiply together, seconds go away, and you end up with meters. So the area under a VT graph is your displacement, is your x, change in x. Okay? And the area under an AT graph is your average velocity. So if this was a number 2, and here we had number 3, 2 times 3, 6, you're going 6 meters per second. Or that's your average velocity for those 6 seconds. They might ask you about instantaneous velocity. If we have a curvy position time graph, you can't find the overall slope without using a front integral, and we don't do that here. So you pick a point on your curve, you draw a line tangent to it, and then you find the slope of that tangent line, and that is your instantaneous velocity. All right, now let's look at acceleration time graphs. Acceleration. In AP Physics B, we only look at constant acceleration or zero acceleration. So we only have straight lines across for acceleration. They can be at zero if you are not accelerating, which means you're going at a constant velocity. Or you could be going faster or going more in the positive direction. Or you could be going more in the negative direction. Okay? Now this can mean you're going faster in the positive direction or you're going slower in the negative. It just means that you're going more towards the positive direction, and we'll look at that a little bit more later on. All right, time always goes on the x-axis, so this y-axis will be your acceleration, your velocity, or your position. All right, so your acceleration time graphs can only be flat. Velocity time graphs can be flat, or they can have a slope up or a slope down. So let's say you're speeding up while going in the positive direction. So you're going in the positive direction, so you're in the positive part of your graph, and you're speeding up, so your velocity is increasing. If you're going in the positive direction, but slowing down, then your velocity is getting smaller. So let's say this is number 5, and this is number 2. You got smaller, your velocity got smaller. Now you're going in the negative direction, so you're going west, but you're speeding up going west. Then you're going to be getting a bigger number, but in the westerly direction. So here you have negative 5 versus negative 2. See, you're getting faster negatively. Slowing down in the negative, same idea. Now, if you're throwing something in the air, let's think about how something moves if you throw it just up and down. You throw it up, it leaves your hand at some velocity. Now it's a velocity upwards, so it's positive. And as it travels up, it slows down until it reaches its highest point. And at its highest point, its velocity is 0. It slowed, it stopped. And now it changes direction. And it starts coming back down, and it goes faster, 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 faster. So that's a nice idea. Now if you have a flat velocity, that means you're going at a constant velocity, which means you're covering the same distance every second. Now, same distance every second, here's an example of that. Okay? This first graph up here, you are covering 10 meters every second. Bam, 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 bam. Okay? That gives you a position time graph that's straight up like that. Straight up at a slope. Your slope will be your velocity at that. Okay? So remember, xt graph, that's your velocity for slope. Okay? So you cover 10 meters every second, plot it out, works out prettily. Now, let's say you are accelerating, which means you have a positive acceleration while traveling in a positive direction or something like that. You are accelerating. If you're accelerating, you're going to have a curve. You could have different curves. You could have it curve up like it is there. You could have it curve down. You could do this, and you could do this. Okay, it just depends on what you're doing. You're going to have a curve of some kind depending on your type of motion. Okay? So in this case, you're traveling faster. You're covering more distance every second, so your position is increasing. So the distance between here is smaller than the distance between here because you're covering more distance. If we look at this third graph, the position time graph down here, we say, okay, what's going on? It looks a lot like the second one, but a little bit different. Our position initially is far away from the origin, far away from 0. Okay? And then we start traveling back until we get to 0. And because it's curving, you know, initially you don't cover much distance. But then, you cover a little bit more. Okay? There we go. We'll leave it at that. See, at first, you don't cover much distance, but then you cover a little bit more. All right? So you cover more distance as time goes on. If you're below the axis, it's the same idea, same type of graphs. It's just now you're doing it in the negative. So if, let's say, we were accelerating this way, so we're starting here and accelerating down, and we kept going, we would just keep going in the negative direction. But that means that you are now traveling negative past the origin. Okay? You've passed your starting point. Now, when you're doing this, you look at acceleration to describe your velocity or your change in velocity. You look at velocity to describe your position. Do not link acceleration and position directly without considering velocity, and I'll show you why. All right. Now, when you're doing one graph to the other, think of it in terms of pushing. A positive acceleration pushes the velocity to be more positive. A negative velocity would push the position to be more negative. Okay, so you look at it as a pushing. So in this first set, let's say we're going to use this smiley face right here. This is where we're going to start. So our initial velocity starts here. Now we are accelerating in the positive direction. So we are going more positive. So we push our velocity up. And how far it goes up would depend on the numbers. Then we have a 0 acceleration. We're not pushing. So velocity is not changing. And then we have a negative acceleration. It's bigger negative acceleration than the, positive one was. So we have a steeper slope down. Whee! Okay? Now, if we look at our position time graph, we are initially going in a negative velocity. So our graph will initially start going down. But it's pushing it towards the positive, right? Slope up, it's pushing x towards the positive. So I'm going down, but I'm getting pushed more towards the positive. See how that works? Okay, and depending on how long it happens, I could, curve up, or I could not. Now, when you have a constant velocity, it's still pushing it in the positive direction, but it's pushing it steadily in the positive. So you end up with a straight line. Okay? And then it's pushing it negatively down. So then you start getting pushed, so pushing curvy down. So if you have a straight here, then you will have a slope here. If you have a slope here, then you will have a curvy here. Okay? Now here's an example. From the graph, we want to determine the acceleration at 3 seconds. So at 3 seconds, we're at this point. We can find the slope of this line. Slope is change in y over change in x, which in this case is change in v over change in t. So change in v is 4 to 0. Final minus initial. Change in t is 4 to 2. So we end up with a slope of 2 meters per second. If we want the total displacement, we find the area under the curve. So the area under the triangle, 1/2. 4 minus 2 is 2, times 4 minus 0 is 4, plus the area under this part. So that's a 6 to a 4. So that's 2 times your height, which is 4. So you end up with 4 plus 8, 12 meters. So this person, or this thing, went 12 meters and has an acceleration of 2 meters per second at time 3 seconds. Now if we want to draw an xt graph, we say, okay, we're sloping upwards, our velocity is getting pushed up. And it's getting pushed up at an angle. So we're going to curvy up. And then it's going flat. So our velocity is still pushing it, but it's pushing it constantly. So you end up with a straight line. The A versus T, well, we know we're accelerating. We're accelerating at 2 meters per second right there because we have a slope. Here, we have a slope of 0. So there you go. Good luck.